Now, before we go any further, I should perhaps warn you about a common mistake that novice physicists use in a situation like this. So let's say your evil lecturer has told you, work out why cars aren't more efficient, or how does a car burn energy? A common approach that novices take is, I need an equation. I need an equation to work out the energy of a car. So then you go through the textbook looking for an equation that has the right variables to feed it in. I know it's how I got through some of my undergraduate study, but it's actually not a very useful technique. In fact, it's a very dangerous technique for this sort of problem. A common mistake in this situation will be, for an equation hunter, would be, okay, we need to work out how much energy it takes to drive to Sydney. What's an equation? And they might, in fact usually do, come up with the equation, kinetic energy equals half mv squared. So they then plug in the velocity and they think they've done it. And they're then surprised when they don't get a very good mark. So what's wrong with this approach? Sure, I mean, this is a valid equation. It tells you energy depends on velocity. So you can work out what the velocity of a car driving to Sydney is and get an energy out and write it down. Why isn't that right? Well, the problem is that equations come with meaning and words. They're not just disembodied things that float around in space. Now in this case, this equation, sure, it relates energy to velocity, but there are many other equations that relate energy and velocity. It's got some words that come with this one. This is the energy that it takes to accelerate an object from rest up to a particular velocity, or it's the energy that if an object is travelling at that velocity and hits something, that it can be dissipated in some other form. So those are the words that go with this equation. So that's telling us that this is not the energy needed to drive to Sydney, it's the energy needed to get the car up to a particular speed, or if the car is going at that particular speed, it's the amount of energy you'd have to dissipate somehow to slow it down from that speed. And that's not the same thing as the energy needed to drive to Sydney. In fact, what this equation is telling us is the energy needed to start or stop. So let's work that out. Let's imagine we've got our car and it's starting at rest, and you put your foot on the accelerator and go up to driving to Sydney speeds, which is 110 kilometers per hour. What this equation can tell us is how much energy it will take to accelerate the car from 0 to 110 kilometers per hour. It won't then tell us how much energy it needs to stay at 110 kilometers an hour, how much to go up a hill, how much wind resistance, how much friction. That we'll have to calculate separately. But this is the starting energy. Okay, so let's do the calculation. First thing we're going to need to do is convert all our units into SI, System International units. So kilometers per hour is not an SI unit. To convert that into the SI unit, which would be meters per second for velocity, so it's 110 kilometers per hour. So we'll convert it to meters, so there are 1,000 meters in a kilometer. And instead of hours, it should be per second. So there are 60 seconds in a minute and 60 minutes in an hour. So we have to do this, which comes out at about 30 meters per second, roughly speaking. Remember, this is a ninja calculation. We're not going to worry about whether it's 30.01 or 29.56 or something like that. There are many other approximations we're going to make that are much worse than that. So if we start obsessing about the exact decimal places here, that we're focusing on the unimportant things, and we're using up brain space that could be better devoted to focusing on the more important things. Okay, so that's this. How much does a car weigh? Well, cars are typically, you look this up, between 1 and 2 tons. Or a ton, metric ton, is 1,000 kilograms. So cars have a mass of 1 or 2,000 kilograms. Let's call it, in this case, say 1,500 kilograms. Be typical for a fairly small car. Okay, so the energy needed to start is going to be half times the mass of the car times kilograms, not kilometers, 1,500 times 30 squared, which comes out as 675,000 joules, which we'll call roughly about 7 by 10 to the 5 joules, which is roughly a million joules, 1 megajoule. So roughly speaking, accelerating a typical car up to freeway speed takes about 1,000,000 joules, about a megajoule. Now, of course, this will depend a bit on exactly how heavy the car is, but that's a good ballpark figure. 1 megajoule, that's a lot of energy to accelerate the car. Now, how many times do you need to accelerate a car up to the speed to drive to Sydney? Well, in principle, if you're very lucky, don't get all the traffic lights as green and there are no traffic jams or roadworks, only once. You need 1 megajoule to accelerate up to 110 kilometers an hour at the start, and then you can just cruise at 110 kilometers an hour all the way to Sydney. Realistically, you're going to hit some traffic lights and roadworks and things, so you might need a few of those things. So starting and stopping is going to be a few megajoules. Is that going to dominate? Well, we don't know yet. We're going to have to compare it to some other numbers. That's another thing most ninja physics calculations involve, comparing things. So this is form of energy. We'll now go and work out some of the other things and see which is most important.